All right, so the last segment of chapter 3 that we're going to talk about is really if the observed ratios that we see out in nature or in a certain population or in a sample actually deviate from Mendelian law or from what is expected. And the way we do this is by using a goodness of fit test, also known as a chi-square test. And this answers the question, does the data that we observed actually fit with Mendel's laws? So, for example, we're going to use the two flowers here that have been or that are serving as the parent generation. So we have a purple flower. We're crossing that with a white flower. In the F1 generation, we get 100% purple flowers, and then we allow that F1 generation to intercross. And in the F2 generation, what we end up with is a total of 105 purple flowers and 45 white flowers. So our question then becomes um, does the numbers that we saw in this example match what we should have seen according to Mendel's law? So to test that, we actually have to form our hypotheses as the first step. So our null hypothesis states that is no difference between the observed and the expected phenotypes for that flower example. And hypotheses always come in pairs. So the alternative hypothesis takes the opposite stance of the null hypothesis. And in this case, it states that there is a difference between the observed and the inspected phenotypes in the white and purple flower example. So the way that we test this is by setting up what we observed and calculating out what we should have expected. So the way I like to set this up is by creating a table. In our first column on the left-hand side, we've got our phenotype, so purple, white, and then the total. The next column is going to be the observed. So the data that we were actually provided. So we know that we saw 105 purple flowers, 45 white flowers for a total of 150 flowers. And then in the third column on the right hand side, this is where we calculate the expected percentage of, or the expected number of flowers that we would expect to show up according to Mendelian law. So, looking at the purple and white flowers in a regular dominant recessive relationship, we would expect 3/4 of the offspring in the F2 generation to be purple. So, we take our total flowers in the study, multiply that times 3/4 or 75%, and we get a total of 112.5 plants that should have been purple. And then we do the same thing for the white flowers. We'll take the 150 total plants observed in the study and multiply that times 25% or 1/4, and we should have gotten 37.5 flowers that should have been white. So now that we have our observed and our expected numbers, we can then proceed through the chi-square analysis. So chi-square is going to be designated as x squared, and we're going to follow this equation here. So the sum of the observed minus the expected squared divided by the expected. So in this case, our chi-square value, we're going to look at two sets of numbers and then add them together. So our first set of numbers has to do with our purple flowers. The second set of numbers has to do with the white flowers. So with our purple flowers, we know that we observed 105, but we should have expected 112.5. So we'll take the difference and square it, and then divide that product by 112.5. Likewise, with the white flowers, we observed 45. We should have expected 37.5. We'll take the difference and square it, and then divide that product by 37.5, or the expected amount again. So once we work through all of that math, we then will add up our two chi-square values. So we end up with 0.5 for the purple flowers, 1.5 for the white flowers, for a total chi-square value of 2.0. So x squared equals 2.0 here. And one other piece of information that we actually have to have is identifying our degrees of freedom. So our degrees of freedom are always going to be the total number of phenotypes that are involved minus one. So we have two phenotypes, purple and white, for a total of two phenotypes. So 2 minus 1 is 1. So in this example, our degrees of freedom equals 1. And we're going to use a p-value in the chi-square distribution, as you can see on this chart. This is table 3.7 in your book. And we're going to be looking at the column that is highlighted as 0.05. So this is our cutoff value. So the way that we find the critical chi-square value is by designating our level of significance across the top, which is always 0.05, and then lining that up with our degrees of freedom over here on the left-hand side. So we know we had 1 degree of freedom, and we're using a cutoff value of 0.05. Therefore, our chi-square value is 3.841. And we know that the p-value that we calculated was 2.0. Therefore, the p-value was actually less than our expected chi-square value. So what does that mean? The p-values, if it's less than 0.05, then we're going to reject our null hypothesis. And that states that there is a difference between the observed and the expected data. If the p-value is greater than 0.05, then we failed to reject, or you can think of this as accepting the null hypothesis. And what this is really stating is that there is no difference between what we observed and what we expected. So our cutoff value was 3.8. That was our chi-square value. The actual chi-square value that we calculated for our data set was 2.0. Therefore, our p-value ended up being less than 0.05. So hang on, sorry, I have to think about this. So we end up rejecting the null hypothesis in this example. All right, so that's how you work through a chi-square test. We're going to do this in class as well, so don't get too nervous about it, but I just want you to be exposed to it before we actually start through the activities. All right, that is the end of the Chapter 3 material, and we will see you guys in class.